All right, let's talk about something that can quietly, and I mean quietly, bring your whole Postgres database to its knees. This is a huge deal, especially now when we're all using Postgres for pretty much everything. Running our main app, crunching analytics, and of course, managing our background job queues.
And this quote, man, it just captures the danger perfectly. This isn't some big, loud crash where all your alarms go off. Nope, this is a slow burn, a quiet degradation. Your system just gets a little bit worse every day. Your performance starts to sag, and your monitoring tools, they probably won't even notice until it's way too late.
So, what is this silent killer? What's really going on under the hood? Well, that's the mystery we're going to unravel right now. We're going to look at the evidence, we're going to identify the culprit, and most importantly, figure out how to stop it. To crack this case, we have to start at the scene of the crime. And that scene is something a lot of us use every single day. A good old-fashioned database job queue. You know what I'm talking about, right? All those background tasks your app needs to run, sending emails, processing images, you name it. A job queue table is perfect for that. You pop a new job in as a row, a worker grabs it, does its thing, and then the row gets deleted. The table itself doesn't really grow, but the amount of data flowing through it is just massive. It's a constant churn.
And the life cycle for each job happens at lightning speed. A row gets inserted. A worker query finds it and locks it so nobody else can touch it. It does the work, and then, poof, deletes the row. Insert, select, delete, over and over and over, thousands of times a minute. It's simple, it's efficient, and it works. Well, until it doesn't.
Now, here's where things get really interesting. The whole problem, our first big clue, is hiding in that very last step, the delete. To see why, we've got to pop the hood on Postgres and uncover some, let's call it, hidden evidence.
Get ready for this, because it's a bit of a mind-bender. When you tell Postgres to delete a row, it doesn't actually delete it. Not right away, at least. And I know that sounds completely bonkers, but it's the key to one of Postgres's most amazing features.
That feature is called MVCC, which stands for Multi-Version Concurrency Control. It's this brilliant system that lets tons of different processes read and write to the database all at once without stepping on each other's toes. It's like a time travel machine for your data. It keeps old versions of rows hanging around so that a long-running query can see a consistent snapshot of how things looked when it started. And this brings us to our smoking gun, the dead tuple. A dead tuple is basically the ghost of a deleted row. It's been marked for deletion, so no new queries can see it, but is still physically sitting there on the disk taking up space. It's a ghost in the machine.
So you've got these two completely different realities happening at the same time. On one hand, your application asks, hey, how many jobs are pending? And Postgres says 3, and shows you just 3 rows. But what Postgres actually had to do was wade through a graveyard of hundreds, maybe thousands, of these invisible dead tuples, just to find the 3 live ones. All of that is wasted work. And it's what starts to slow everything down.
Okay, so if these dead tuples are the problem, you're probably thinking, why doesn't Postgres just clean this mess up? Well, it's supposed to. It has a cleanup crew for this exact job. But sometimes that crew is prevented from working, and that's how we find our prime suspect. Yep, this cleanup crew has a name. It's called autovacuum. It's a process that runs in the background, and its entire purpose in life is to find these dead tuples, get rid of them for good, and keep the database nice and tidy. But here's the catch, the big gotcha. Autovacuum has one critical rule it can never break. It cannot clean up any dead tuple that might still be needed by a transaction that's currently running. The oldest running query in the whole database sets this thing called the MVCC horizon. You can think of it like a line in the sand. Autovacuum is forbidden from cleaning anything on the newer side of that line. So let's watch the crime happen in slow motion. Picture this. Remember our database is doing everything at once? Okay, so some big, slow analytics query kicks off. It's going to take a few minutes to run. No big deal, right? Wrong. The second that query starts, it slams the brakes on that MVCC horizon. It draws that line in the sand, and for as long as that query is running, that line cannot move forward. It is pinned. Now, all the while, our super fast job queue has no idea this is happening. It's just humming along, churning through jobs, inserting and deleting, creating thousands and thousands of new dead tuples behind that pinned line in the sand. And bam, autovacuum comes along, ready to do its cleanup job, but it sees that pinned horizon and it just stops dead in its tracks. It's completely blocked from touching any of that new waste.
The dead tuples just start piling up, higher and higher, and your database starts to slowly, painfully grind to a halt. So the real villain here? It's not the queue. It's the slow query holding the whole system hostage.
So, we've found our culprit. We know how the crime happens. Now, let's talk about the resolution. If the problem is these two different workloads crashing into each other, the solution has got to be some form of traffic control. Now, you might be thinking, just use a timeout. Postgres has tools like statement timeout, but they're kind of like a sledgehammer. They can kill one single query if it runs for too long. The real sneaky problem here isn't one super long query. It's lots of overlapping medium-length queries. Imagine 3 reports that each take 40 seconds, but they start 20 seconds apart. No single one is long, but together they keep that horizon pinned down continuously. Your timeouts won't fix that.
This is where you need smarter traffic control. Maybe you use a connection pooler to limit how many analytics queries can run at once, or build a queue in your app. And the proof is right here in the data. Just look at these numbers. It's night and day. Without any control, the queue backlog explodes to 155,000 jobs, a total death spiral. But by simply limiting the analytics query so autovacuum can breathe, the backlog is 0. The system is perfectly stable. It's a staggering difference.
So what does this all boil down to? What's the big takeaway? It's that this isn't some weird theoretical edge case. In today's world of just use Postgres for everything, this is the new normal.
And I think this quote from the source material just hits the nail on the head. When you have a fast, high-churn workload, like a job queue, sharing a database with a slow, analytical workload, this kind of conflict is basically inevitable. The real danger isn't that your database will crash, it's that it will just degrade quietly.
And that really leaves us with one final, pretty important question you should be asking yourself. This silent killer, it's patient, and it doesn't set off any alarms. So, is it possible that your database right now is also quietly degrading?